Okay, let's continue our discussion for problem number 2 for this. We're now on this average stress increase in the clay layer below the corner of the center of the rectangular area. So as mentioned a while ago, we make use, since we are talking about consolidation settlement, we go back to our soil mechanics on the computation for consolidation settlement that we have discussed before. So we have this equation for the average stress increase of the corner below the corner of the rectangular area. So we have to identify our H2 and H1, our I's, our I for our H of 2 and H of 1. So our H of 2, of course, from our figure is 5 plus 40 plus 18. Our H of 1 is 5 plus 40. So based on that, we have identified our H1 and H2. We have to identify our I for H1 and H of 2. This is the influence factor. So based on that, we're going to use a certain figure in chapter 5 in this book. However, this was already discussed in our soil mechanics, that to get the value for our I, for the influence factor, we have to get the value for m sub 2 and n sub 2. So how to get for m sub 2 and n sub 2? You have this equation, m sub 2 and n sub 2, we are referring to B all over H2 and L all over H2. So if you're going to simplify, this is 0.71 and this one is 0.95. So based on the figure that is found in chapter 5, that is figure 5.17, once we have the value for n sub 2 and n sub 2, according to our discussion in soil mechanics, we have the value for I, the influence factor, which is 0.21. And this is for H of 2. For H1, the influence factor is you make use of B all over H1 and L all over H1, respectively for M2 and N sub 2, and the value is 1 and 1.33. We locate again on our figure 5.7, the M2 is 1 and N sub 2 is 1.33. Based on that figure, as we discussed in soil mechanics, that is equivalent to how to locate that one. It was discussed in soil mechanics. So we obtained that 0.225. So therefore, if we try to substitute to compute for the average net stress at the below the center of the rectangular area, you simply have to substitute the value, and now we obtain 615.3 pounds per square feet. So after that, since we have now the stress increase below the center of the rectangular area, so the stress increase below the center of the mat foundation is 4 times this average, and we give us 2,461.2 pounds per square feet. So therefore, our settlement for this, the settlement for our mat foundation is equal to the expression to this expression. You simply have to substitute the value of these parameters. This one is given, this is given, this is also given, this one was solved, you also solve this one. Simply have to substitute this specific values, and we obtain our value for the settlement for the mat foundation is 6.68 inches. Now we move on to the structural design of mat foundation. So for the structural design of mat foundation, we have a conventional method. This is conventional rigid method. So we're going to make use of the conventional rigid method, the most commonly used method for structural design of mat foundation. So how it is being done? So we are given with a certain conventional rigid mat foundation design. So this is a mat foundation design. It has 12 columns in this particular figure. And if you're going to have the column load for each line, so it is illustrated here. If you isolate this one, I, H, G, and F, so you have here our illustration, which contains our column loads. And of course, for this one, we have here, of course, this is the edge of the mat foundation. So if we're going to have the critical perimeter section, so this is from the edge of the mat foundation, so we can have here this specific parameters within the perimeter of this column. This is also an illustration to illustrate this critical perimeter. So critical perimeter column. So this is another illustration. This is the edge of the mat. So this is how it illustrates our critical perimeter column. For the critical internal column, so this is how it is being illustrated. So for this one, this is B sub O that equal to 2L prime plus L double prime. So this one is B sub O, L prime plus L double prime. And this one for this critical internal column, B sub O is equal to 2 L sub prime plus L sub double prime. So for this conventional rigid method, we have here the following steps. So the first one, you have to calculate the column load. You simply have to add the total column. The second one is you obtain the pressure on the soil. So pressure on the soil, which is below the mat at points A, B, C, D by using the equation. So for this one, this is the equation for the pressure on the soil. Q, of course, you're familiar with this. We will encounter this in our fluid mechanics computation for the pressure in a certain structure. So we're given with the area, B times L, we have the moment of inertia above the x-axis, moment of inertia above the y-axis, and you have your moment of column loads above the x-axis, which is equal to Q times E sub y. We have the moment of column loads above the y-axis, which is Q times E sub x. The load we have the load eccentricities, E sub x and E sub y in the x and y directions, which can be determined by using x prime and y prime coordinates. So for x prime coordinates, we have to identify how to compute this one. You review your statics of rigid bodies and strength of materials. You simply, to get your x prime, you have to multiply each of the column loads to the distance from the center of each column load towards the reference point. This is all over the total column load. And so that you can get, why we have to get the value for x prime, so that you can get your E sub x, your eccentricity along the x direction, and that is equal to x prime minus b all over 2. And similarly, your y prime is equal to, this is equivalent to each of the column load multiplied to the distance from the center of the column load towards the reference point along y direction. You have to take note, this is along x direction, this is along y direction, then all over the total column load. So basically our E sub y is equal to, this is equivalent to y prime subtracted by L over 2. So afterwards, after you have computed for the eccentricities, S of x and S of y, you simply have to compare the values of the soil pressure determined in step number 2 with the net allowable pressure to determine our Q that should be smaller than the net allowable bearing capacity. So we have to divide the mat into several strips in the x and y direction. So of course we have to let the width of any strip be our d sub 1. Then afterwards, we have to draw the shear and moment diagram for each individual strip in the x and y direction. For example, the average soil pressure, the bottom pressure in the x direction, based on our figure, and the bottom direction in our mat foundation, this is the bottom direction, this is the bottom strip. So considering this one, you have I, H, G, and F. So to compute for the average soil pressure, that is equivalent to Q sub I plus Q sub F all over 2. So basically, our Q sub I and Q sub F, those are soil pressure at points I and F as determined from our step number 2. So for this one, the total soil reaction is equal to, you have to take note that is equal to Q average B1 times B sub 2. And we try to obtain the total column load on the strip as Q1 plus Q2 plus Q sub 3 plus Q sub 4. And basically if the sum of the column loads on the strip, of course it will not be equal to the Q average B1 times B, because the shear between the adjacent strip has not taken into account. So since our Q average B1 times B is not equal to the sum of the column strips Q1 plus Q2 plus Q3 plus Q4, we have to make some adjustment. So the column loads need to be adjusted. So we are going to adjust, so we're going to compute for the average load, which is Q average B1 times B. Of course, B1 is located, this is our B1, from there to one column to another column, so that is B1. Our B is the width of the foundation, of course. Then plus our column load on that particular strip, you have Q1 plus Q2 plus Q3 plus Q4 all over 2. So this is now the modified soil reaction. So the modified soil reaction, you have here Q average is equal to average load all over Q average B1 times B. And the column load modification factor is, you have F. This is now the column load modification factor. F is equal to the average load all over, this is the average load. The average load all over Q1 plus Q2 plus Q3 plus Q4. This is the total column load for a particular strip. So the modified column load now would be equal to FQ1 plus FQ2, FQ3, and F sub Q4. So this is now the modified column load on a particular strip. For example, if this is a strip, one strip, another strip. So meaning to say, this is isolated bottom strip. So this is now, if we're going to have Q1, Q2, Q3, and Q4, since there is a presence now of F, so meaning to say this is now the modified column load. So as being completed here. So this modified column loading on the strip under consideration, of course it was shown a while ago. So the shear and moment diagram for the strip can now be obtained. So after that, after you have obtained the modified column load, you can draw the shear and moment diagram. So afterwards, on the next step, you have to identify the effective depth, which is our D, using the equation from the American Concrete Institute, the factored column load equation. So using this equation, you can compute for the effective depth of the mat So this is denoted by small letter d. So afterwards, you have to take note that the expression for B sub O in terms of D, which depends